Good morning. In this lecture video, as I explained, construction of Moore state diagram for Moore model, state table, and the transition table. So, sorry. In this video, I'm going to explain remaining part, that is construction of excitation table. Okay, excitation table from transition table. As you know, excitation table is analogous to excitation table is analogous to transition table. It also consists of present state, in place of next state, excitations. So here we use Q1, Q2. So we use state excitation variables as D1, D2 when x is equal to 0 and then when x is equal to 1 and output. So just we copied output here. Okay. So again, so these excitations are complete written. D1 based on the transition from Q1 to Q1 plus. Again, D2 is based on the transition of Q2 to Q2 plus. So we consider application table. Application table of D flip-flop is for transition Q2 to Q2 plus, for 0 to 0, 0, 0 to 1, 1, 1 to 0, 0, 1 to 1, 1. So again it is same as next state, that is Q plus. Okay, so here we d1 plus d1 when x is equal to 0 is equal to q1 plus when x is equal to 0. So just copy it, and d2 is equal to q2 plus. Similarly, when x is equal to 1, d1 is equal to q1 plus and d2 is equal to q2 plus. So we copy these values here. Okay, so this is what excitation table. Okay, so from the excitation table, expressions. So just consider only d1. Again, d1 depends on two state variables q1, q2 and x, input x. So three variable map is required. Three variable. Clear now? And these are the values we should write in the first row, that is when x is equal to 0. Okay. So here when q1, q2 represent columns. So 0, 0, 0, 1, 1, 1, 1, 0. See, when q1, q2, 0, 0, the entry is a 0. When 0, 1, 1. And when 1, 0, a 0. And when 1, 1, it is 1. Similarly, these are the d1 values when x is equal to 1. So, this we will enter in the second row. That is when x is equal to 1. So, when q1, q2 is 0, 0, entry is 0. 0, 1, 0. 1, 0, 1, so 1. So, here it is 1. For 1, 1, 0. So, it is 0. Clear na? So, here since we need to write product expression, SOP expression, we do the grouping of ones. So, here one pair is possible. Corresponding product term is x bar and common is q2, and here one isolated 1. So, the corresponding product term is x q1 q2 bar. So, the expression is x bar q2 plus x q1 q2 bar. Clear? Similarly, when considering d2 column, okay, and the three variable map. See, first row all zeros, second row when x is equal to 1 all ones. So one quad is possible. The corresponding expression is d2 is equal to x. And for z, see, no need of k-map. Otherwise, if at all, if you want to use k-map, means only two variable map, because z depends on only q1, q2. So we can directly write the expression when x output is 1. So at that time, the value of q1, q2 is 1, 1. So it is z is equal to q1, q2. So we can write expression for z directly without k-map. Okay. So as you know, next step is to write the logic diagram for these expressions. Okay. these are the expression, right? Again here we need two flip-flop D1 D2 D1 D2, and this outputs are Q1 bar, again D2 Q2 bar. Control inputs are connected to common clamps. Okay, and see the requirement for D1. Here we require one two input AND gate, one OR gate, and three input AND gate. Okay, so see one OR gate, inputs to the OR gate is from output of AND gate, another output of another AND gate. So see the first two input AND gate inputs are, it is derived from X bar, right? X bar, and another input is Q2. This is the Q2 line. Q2. Clear now? And for D2 it is directly connected to the line X. And outputs of AND gates are connected to OR gate, and its outputs connected to D1. And for Z it is Q1 Q2. So AND gate is required. One AND gate, output of AND gate is Z, inputs to the AND gate is, so one line from Q1 and another line from Q2. Here it is from Q2 and here Q1. Okay, yeah, fine. See the design sequence what we discussed in the previous videos. So that is called sliding window sequence detector. Sliding window sequence detector. That means we use a window. We use a window. Suppose if you want to detect a 101, we make a window of 101. In the received sequence, we place the sliding window. If it is matches, output is 1. If it does not matches, output is 0. Okay? So that is called sliding window. So these windows can be overlapping or non-overlapping, as we discussed. 101 sequence, the last one is overlapped with the first one. Right? So another methods are there in contrast to sliding window, that is disjoint window. Disjoint window sequence detector. Here it divides the input sequence into windows of fixed length. Windows of fixed length. Okay. So normally the length of the sequence to be detected, I mean the window size is equal to the length of window, the length of sequence to be detected. So it recognizes the input sequence when confined to the one of the windows. So suppose if a window is longer than the sequence, change sequence to be recognized. I mean sequence to be recognized are changed. Let's see example for 101 sequence in a disjoint windows of length 4. The sequence will be changed to, see the changes sequence. We add first 0 or first 1, and last 0 or last 1 to make the size 4. To make the size, that means if we receive 0101, output is 1. Otherwise 1101, output is 1. Otherwise 1010, output is 1. 1011, output is 1. So that means we add first 0 or 1, otherwise last 0 or 1 to make the size equal to length of the windows. Okay. Again, design with the disjoint window is more complex than the sliding window concept, because the detector must be record where the bits occurs within the window in addition to detecting the sequence. So let's have a look into the different 101 sequence detector. See, this is sliding windows overlapping. Sliding windows overlapping. See, your output is 1, correct? So this one is overlapped. This one is overlapped. Okay. Again, this one is overlapped. Right now, again this one is overlapped. So this is overlapped. If it is non-overlapping, here it is 1. Okay. Again the sequence 101 is there, but it should not overlap. It is a non-overlapping. That is why it is not overlapped. So we consider output 0 here. Again new 101 sequence 1. Again new 101 sequence 1. Again see here, we can make this 101, but here 1 should not be overlapped. So this we have not considered. Again here 101. This is the same input sequence. Here more number of times output is 1, but here less number of times, because here overlapping is applied, here overlapping is not applied, that means non-overlapping. Okay, and others, sliding windows overlapping initial one, means for initial one output is 1 and overlapping is allowed. So here it is 1, again this is overlapped, this is 1, again 1, like that. Okay. And sliding windows non-overlapping in initial 1. See, so initial 1 output is 1, correct? Right? Here initial 1, again for 101 we made output 1 because overlapping is allowed. Here non-overlapping, for initial 1 we made output 1. So again we have not made output 1 here because it is a non-overlapping. So we consider these 101 as a output 1. Again 101 output 1, like this. Is clear now? And disjoint windows. Disjoint, as I said now, the input sequence is divided into uh, 3 bits, means the sequence to be detected, the length is 3 bits, no? So we divide it into 3 bits. Okay, so for first 3, this is 0 1 0, so output is a 0, correct? Again next is 0 1 1 0 1, output is 1, 0 1 1 0, so here it is 1. Okay, again 0 1 0, so all output is 0 1 0 1. So here, I mean, whenever the output is detected, it will reset. It will reset. I mean, starts from the first bit. Start from the first bit. No overlapping, nothing. It will reset. It will go to the reset state. That is called disjoint window. Clear na? So we'll discuss one more problem on disjoint windows in the next video. Uh, Thank you all. I'll continue in the next video.